All right, class, welcome back to the unit on similarity and the lesson on similar polygons. This is the third installment of this particular lesson because we've done two previous videos regarding similarity with polygons. We've talked about using scale factors and using similarity and understanding it. But now we're gonna complete the whole thing by getting into some cool mixture of algebra and geometry. We get into equations with more scale factors and more using similar polygons. So let's jump right in and we'll finish this. If anything that I say in this video is confusing, make sure you go back to see the two previous instructional videos. So here's where we begin using similar polygons. We're going to dive right into similarity, remembering that with similar polygons, angles are congruent, corresponding angles are congruent, but corresponding sides are proportional. So in these two polygons, we already say it's given that they are similar. How do we know? This little thing means similar. So what do we know? We know that the corresponding sides are proportional. So what this means is that we can set up a whole bunch of proportions on the sides. So in the small polygon, we have side ED, right? We can compare that to the same side in the large polygon. And the same side in the large polygon is DA, okay, so or AD, so it doesn't matter. So that we know that we have a comparison of ED to AD. And what that is going to equal, it's going to have the same proportion as the smaller polygon, EF, to the same corresponding side in the larger polygon, AB, and that will be equal to, again, the small polygon, FG, compared to the same corresponding side on the large polygon, BC. Now we know that to be true because we understand proportionality. We understand that corresponding sides are proportional. So now what we can do is figure out the values of x and the value of y. Okay, so with this proportion, we know a whole lot of stuff. Because the small polygon from ED is 6, and in the larger polygon, the similar corresponding side is 9, and that would be equal to, because it is proportional to, the length in the small polygon being y, and the length of the large polygon being 5. And so what we can do is solve for y, and we can do the same thing and solve for x. 6 to 9 would be equal to the ratio of the small polygons FG and the large polygons BC, so it would be x to 7.5. So now we have our two equations that are set up to find the values of x and y. And now what we can do is use cross products, and we'll figure everything out. So when we use cross products, we will have 9y being equal to 30. Therefore, y would be equal to 30 divided by 9, which is a crazy number, but that can be simplified. So the value for y can actually be simplified. Okay, so both the numerator and denominator are divisible by 3. So we'd have 10 over 3, or 3 and 2/3, or 3 and a third, excuse me, or 3 and a third, or 3.3 repeating, whatever you want to call it. We now know the value of y. Okay, so all of these are accurate values for y, as long as we use the repeating bar for 3, 1, 3, 3, 3. So we have now figured out the value of y. Now we can figure out the value of x, doing the same thing. So again, cross products, 9 times x would be equal to 6 times 7.5. Let me do this on a calculator super quick. 6 times 5 is 30, 42, so that would be 45. Oh, that's a helpful number. Thank you, x, for being a lot simpler. Okay, so 6 times 7.5 is 45. Therefore, x is going to be equal to 45 divided by 9, which is 5. To-do. There's our value for x. So we have now used similar polygons and cross products to solve some algebra stuff. Okay. Now what we're going to do is kind of do the similar concept, but we're going to take a step back and go back to scale. Okay, so we're going to understand similarity, and we're going to use scale to do it. This is probably hard to see, so I'll explain what's going on. The problem reads, a movie theater screen is in the shape of a rectangle, 45 feet wide by 25 feet high. Which TV screen format will show the most complete movie from the theater? So we have a standard format, which is 36 inches wide and 27 inches tall. Okay, so that's the standard format. Then we have the letterbox, which is 36 inches wide and 20 inches tall. Now, which one is going to fit the movie theater's format? Now, what was the movie theater's format? The movie theater's format was 45 feet wide and 25 feet tall. Okay, so the movie theater's format was that. Which TV screen will show it better? And what we can do is look at the ratios. Hopefully, if you haven't figured that out by now, what we can do is look at the ratios and figure out which ratio is closest to the movie theater's ratio. So our ratio of the movie theater, 45 to 25, both divisible by 5, right? So we'd have 9 over 5. That's the ratio of the movie theater. Now we look at the ratio of the standard television screen, and we want to simplify our ratio. 36 and 27 are both divisible by 9, and so we would have 4 to 3. All right, so that's not exactly 9 to 5, right? So the standard TV screen may not fit. Well, what about the letterbox? So let's work on that. We have 36 to 20. Both of these are divisible by 4. Okay, so 36 divided by 4 is 9, and 20 divided by 4 is 5. Look what we have. We have a money winner. The letterbox TV screen is exactly the same ratio as the movie theater, so it is the letterbox screen format that would fit the movie, whatever it is we're watching from the theater. Okay, so we're looking again at scale, we're comparing ratio, and why take that jump back? Because now we're going to get into some fun questions. So this is a question that is fun to deal with. We're talking about design. Your class is making a rectangular poster for a rally. Now the poster's design is 6 inches high by 10 inches wide. Now remember, what we want to do is label everything. 6 inches high by 10 inches wide. That's the design of the poster. Now the space allowed for the poster, like this wall, okay, this wall, the space allowed is 4 feet high, okay, by 8 feet wide. And the question is, what are the dimensions of the largest poster that will fit in this space? So the poster has to keep the same ratio. The poster has to keep the same dimensions. Now, if we look here, we can see that the ratio of the space is 1 to 2, and the ratio of the design is not 1 to 2. Okay, it's 3 to 5. So this is not an exact fit. So what do we do? Well, first thing we should do is think about how are we going to fit that thing in. I want you to think about a text box, like if you ever use a text box, and if you click and drag on a corner, what happens, right? The whole box expands, keeping the same dimensions. Okay, so that's what we're talking about here. We have to keep that in mind as we move forward. So check this out. We're using inches here, we're using feet here, so let's go ahead and fix that. The space we need, not 4 feet, but 4 times 12, 48 inches, and not 8 feet, 8 times 12, 96 inches. Okay, so that's the space that we need. So how in the world can we go from 6 to 10 and fit it to 48 to 96? So what is going to happen as we click and drag, right? We click and drag that 6 by 10, will it fit? So we have to think about scale factor. What scale factor can we multiply by 6 that would get us to 48? And what scale factor can we multiply by 10 to get us to 96? Okay, so we have to ask that. what scale factor can we multiply by 6 to get us to 48? And then what scale factor can we multiply by 10 to get to 96? Now, why did I use an x and a y? Because they might be different. Well, clearly they're going to have to be different. Okay, so we have to think that through. Now, the scale factor to multiply by 6 to get to 48 is clearly 8. Okay, so the scale that we would grow, the height, is going to be a scale of 8. But for the width, the scale would be 9.6. So we can't adjust that because this would distort the original design. So one of these scales has to be used for both the height and the width. Which one is it? So hopefully by now you know it's 8, but let's say you didn't know that. Let's say it would be a scale factor of 9.6 that you think it is. If we were to grow the height by a factor of 9.6, it would be bigger than the space that we need. This would be bigger, wouldn't fit. Okay? So if we multiplied the height by 9.6, it would not fit. So it can't be 9.6. If we multiply the height by 8, it's a perfect fit. And if we multiply the width by 8, it would fit in. We'd have leftover. We'd have 16 inches left over. But that's not the point. That would be the largest poster that would fit. So we know that the scale that we have to use is 8. Okay, so we must use 8 as the factor, okay, as the scale factor. So then the largest dimensions would be, of the design, the largest dimensions would be 6 times 8 and 10 times 8, or 48 inches high and 80 inches wide. That would be the largest poster design that would fit in the space. Okay, so we have to understand all that stuff about scale factor and all that, and get into what's happening. So that would be our dimensions. Now, what about this last one? Okay, so we have a poster that is 6 inches high by 10 inches wide. What are the dimensions of the largest complete poster that fit in space? 3 feet high. My 6th period is starting. Over 4 feet wide. Okay, so how are we going to figure that out? And remember, we're working with inches here, so we should work with inches here. Okay, so we're going to go from 6 to 10. Somehow, we're going to click and drag and make it fit. 3 times 12 is 36, and 4 times 12 is 48. So, again, we have to figure, what is the scale factor? What can we grow the height by to get to 36? So some number times 6 would be 36, and we know that scale factor would be 6. And then what would we grow the width by to get from 10 to 48? Okay? So we would see that y is 4.8. Now, so which scale, 6 or 4.8, will be used to grow the original design? Hopefully you have seen the answer is 4.8, but what if you didn't? Let's say the scale was 6. We could grow the height by 6 and it would fit. But if we grew the width by 6, we'd have 60, and that's way too wide. It wouldn't fit in the space. So the scale must be 4.8. Okay, the scale factor must be 4.8. So when we multiply our height, which is 6, by 4.8, we would get the height of the design, 28.8 inches. So the height would be 28.8 inches. And the width would be, that's height, by the way, and the width would be 48 inches. Okay, so the perfect fit in that design. And that's how we deal with scale and scale factors. And that is it, folks, ladies and gentlemen. That's it for the lesson on similarity and similar polygons. So hopefully you've learned some stuff. If anything was confusing, go back and watch again and practice, practice, practice. See you on the next lesson.